Welcome to our first Fix It Friday video. This example, we're looking at a very common mistake that students make when talking about why a particular substance does or does not conduct electricity in a particular state. So the question is asking about sodium chloride, and sodium chloride is an ionic compound. That's going to be important when we explain what's happening in the question. So the first part of their answer is talking about why, as a solid, the substance does not conduct electricity. And actually, the first part of the answer, up until the comma, is a very good way of answering the question. So they have said that as a solid, the particles are fixed in position. And that's true if we look at an ionic solid. It's going to be a lattice of alternating positive and negative ions, cations and anions, held in place by those strong electrostatic attractions, which is what makes it a solid at room temperature in the first place. So there are my ions. They are fixed in position. So it's definitely true that they can't move. It's okay that in this question the student has simply said particles. In fact, that's quite a good word to use if you're not sure about your wording, because it stops you from saying, for example, the atoms are fixed in position or something else that would be wrong, such as molecules. You could easily also say that the ions are fixed in position. But if I were to melt sodium chloride, then that's not a particularly great picture, but that's what I can imagine is happening. The ions are now no longer fixed in position and they are free to move. However, the student has started to talk in the question about electrons. Now, if I were to look at that diagram, I can't see any electrons. Obviously, it'd be quite hard to draw them because they're quite small. But in an ionic substance, there are no free delocalized electrons. The anions have got electrons in their outer shell. The cations have got electrons in their outer shell. None of them are delocalized. The electrons are still fixed in position on the outer shells and the inner shells of the ions that make up the compound. So electrons, there are no delocalized electrons, and I wouldn't certainly be changing the delocalization by melting the substance. So how can we write about conductivity in a more accurate and simple way? So when you're explaining conductivity, you have three situations. You may be talking about a metallic structure, an ionic structure, or a covalent. But in all those cases, what you need for conductivity are charged particles that are free to move from one place to another. Not to just vibrate in one place, but actually to move. So let's consider the three types of bonding that could exist in a structure and see how that relates to conductivity. In a metallic structure, we've got positive ions which are surrounded by delocalized sea of electrons that come from the metal atoms losing their outer electrons. So for a metallic structure, we can explain the conductivity by saying it is the delocalized electrons that are free to move. And that is the case whether the metal is solid or liquid, because the electron sea is always delocalized. We wouldn't talk about conduction in a gas. You're not going to be asked about that. That doesn't really work, because if you were to turn a metal into a gas, the electrons would actually go back onto the outer shells and wouldn't be delocalized anymore. What about an ionic structure? Well, in an ionic structure, as we've just said, actually we want to say that as a solid, the ions that are not free to move. It does not make sense to talk about delocalized electrons because there are no delocalized electrons in solid or liquid. And then ions are free to move if we make our ionic structure molten, or, as is more likely, aqueous, because it's a lot easier to dissolve an ionic substance than it is to melt it. Keeping the wording simple, free to move, not carrying, not flowing, none of those other waffly words, simply whether they're free to move about or not. And a covalent structure, everything is held together by the sharing of electrons and the attraction between the nuclei and the shared electrons. There are no delocalized electrons or ions in a typical covalent structure, so there is no conductivity, whether solid, molten, or aqueous. So although, for example, I can take something like CO2 and I can dissolve it in water so the particles are free to move, that doesn't mean that it's going to conduct, because the CO2 particles themselves cannot carry a charge. The only alternative to this, of course, is graphite. That is our exception. It's a giant covalent lattice and it contains delocalized electrons because only 3 electrons are being used by each carbon atom in bonds, leaving it with 1 extra electron that does get delocalized. So graphite, we can say the same thing as metals. Delocalized electrons are free to move.